We'll do this later on. Okay. So basically, good morning, everyone. I will be covering on hardware security primitives for AGI applications or AGI devices. Basically, the objective of this program is to have a glimpse of AI hardware, their architecture and design. But if we are talking about AI hardware or any kind of edge AI, the security of those devices are equally important. Okay. So here we are going to discuss about if we have the edge AI devices, what kind of security vulnerabilities are, how we can consider those things, and how we can solve those problems. Okay. So this is what our main objective is. If you talk about this is a brief glimpse of my lab. Yeah, this is the old lab. Now we have been shifted to the new one. So new one is, I don't know, you have to compare whether it's good or that one is good. This looks much better than this one, right? Okay. So yeah, this is the group who are working with me. They are PhDs, Masters, JRF, BTech, and all those places. Okay. If you talk about the cybersecurity, basically the cybersecurity starts from all the domain that starts from the application security, information security, operational security, network security, end user security, and the disaster recovery planning. So if you talk about the security, cybersecurity, that spans from the network to the hardware, cybersecurity does not only mean with the software security. Whatever the software you are running, wherever you are running, you are utilizing some hardware. And if your hardware is not secure enough, definitely there may be some problem. There may be some vulnerabilities. Okay. Okay, so I was talking about there must be several kind of security concern, especially in the cyber security, that can start from the application, information, operational, network, and end user. End user simply means like whatever the hardware we are using. It is on. Hello. Okay. So basically, I will be talking about the end user security in general sense that we can call it the hardware security. So let us try to understand one by one. Okay. Before that, it is really very important. Like whatever the AI we are doing, there could be two kind of AI. The first one could be the cloud AI, which is the conventional kind of AI, and the second one is edge AI. Why edge AI is important, and why we need this kind of AI? That is really very important to understand. If you compare these two things, like the conventional cloud AI, what they are doing, whatever the data you are collecting from any sensor node or any kind of the input signal where you are connected, whether it could be sensor, it could be like camera or any kind of gadget from where you are collecting the data, you are sending that data to the cloud, and then on cloud you are processing those data, and accordingly you are getting the information, you are taking decision based on that. But what is the problem with this one? The major problem with this one is like whatever data you have collected, you are sending to the cloud, and then you are processing it. Might be there could be some latency, there could be some delay. Okay, but if you need a quick response, in this case, edge AI is really very important, because whatever the sensor you have placed here, immediately you are running the AI algorithm on that. You are processing that information on the node only, and you are taking decision based on that, and now you are storing your data into the cloud. Okay, so the basic difference between cloud AI and the edge AI is basically you are processing, like where you are processing your data, whether you are processing your data at the sensor node or you are processing your data at the cloud. So basically these two things are like very like they are very much similar, but the only thing is like the place where you are processing your data. There must be a lot of benefit out of this one. Like if you are using the edge AI, definitely there are benefits. What those benefits are, let's try to understand it. Okay. Yeah, before that, I just wanted to tell you like, okay, what kind of edge AI or could be, or edge AI devices could be, or IoT devices could be. It could be the camera, it could be the electric vehicle, it could be like home automation or any kind of things which can be controlled like remotely, or you are getting some information, some data you are getting to process it. Definitely you can call them the IoT devices or edge devices. Once you have these edge devices, you need to process them, you need to store them. So this is the typical process of the AI or edge AI. Whatever the things you are trying to develop over here, this is really very, very important to understand. I just told you at the beginning, if you are talking about the security, it does not mean only the software security. It does not only mean the network security. Whatever the hardware you are using to process those things, that hardware security is equally important. And whatever the hardware you are making, these all hardwares are made with the semiconductors. Okay, so if you are able to make a good material or good device which can be tolerable, like which can make a secure devices, that is really very important. Some of the 2D materials may be better in terms of security than the other kind of materials. This is one kind of thing that you should know. So if you want to maintain the security, that start from the devices. If you are able to make a very good device, definitely you can maintain the security. By utilizing those devices, you are making the circuits, and those circuits will also be secure enough. And the next hierarchy or next abstraction level will be the gate level, then system module level and the system level. So ultimately, if you are able to make very good device, you can make good circuits, good module and good system, and ultimately you can maintain the security. Only one very important thing that is very important here is the process variability is one kind of problem or reliability concern in any of the devices. But sometimes these variabilities can be utilized as a benefit. How these variabilities can be utilized as a benefit, I will tell you in the later slides. This may, like if you are listening this one, this may look strange, but this is true. If your circuit is unreliable, might be this can be utilized to maintain higher security and the vice versa. Okay, so how to do that, I will explain later on, and how this kind of variabilities or process variabilities are utilized to maintain the security of those devices, I will explain later on. So I was talking about some of the benefit of edge AI as compared to the conventional AI. So this is really very important. Like nowadays, a lot of things are being connected through the cloud, and a lot of data are being extracted, they are being processed, and maintaining the security of those things are really very important. If you talk about the statistics, the market is very high, okay, for even for the software or the hardware market for the edge AI is really keep on increasing as we move towards the automation side. Either it is autonomous vehicle or any kind of sensor kind of things, everywhere you have to add some IoT nodes or some edge AI node, okay, or edge devices, and they are keep on increasing in the market share. Similarly, if you talk about the globally, the computing market is also increasing day by day. So, and if the computing is keep on increasing, maintaining the secrecy of those computing is really very important, because whatever the data you are extracting from your sensor node, if those data are not secure enough, definitely they can create a problem. If someone can extract the data, might be they can manipulate it, they can give you the wrong decision, and might be your system may fail. So maintaining the security of those devices are equally important. That is why you have large number of data, large number of automation, but with this automation, with this large data, definitely security is equally important. How to maintain the security, we will see here. Okay, so I will discuss a few primitives about how you can maintain the security, but yes, maintaining those things are equally important. Yeah, there are some benefits. If you talk about the reduced cost, because why it is reduced cost? Because whatever the data you have received from the node, you're like in conventional AI, you're sending that data to the cloud and you're processing it. So might be you have to process, like you have to send bulk data to the cloud and you have to process it. But if you are processing on the sensor node itself, the processed data may be reduced, and then you have to store only the processed one only. Otherwise, what is happening? You are receiving the data, you are sending there, you are processing it, again you are taking it back and taking the decision based on that. So it may require large hardware, or hardware cost may be increased, more hardware may be required. But if you are processing on the node itself, definitely the hardware will be reduced, and ultimately that we are calling it the reduced cost in terms of area or in terms of the complexity. Scalability means, like, of course, you can scale them down based on your need. You can change the sensor node, whatever, how much complex algorithm you want to implement. Accordingly, you can manipulate it or you can change it. So scalability is one of the features that you can get benefit out of this Edge AI. The third one is real-time analytics. You have, okay, that data you are processing on the node only. So real-time analysis you can get, okay, whatever you have received the data, you pass through AI algorithm, and you are getting the results immediately. You don't have to store into the cloud and getting back the result and before. So you can take decision, you can get the data immediately on the sensor nodes only. So this is one of the benefit of Edge AI. Latency I was talking about, because you are processing on the node only. So there is no latency. Latency means the delay. You are sending the information to the cloud, you are getting back the information, so they may take time. Okay, but if you are processing on the node itself, definitely latency will be less. And similarly, like information security and privacy, maintaining the secrecy of information at the sensor node may be easier than maintaining the secrecy at the cloud. Like whatever you have the bulk data, maintaining the security of those things may be complex than the individual sensor node. It is really very important, like how much security you need, you can increase the complexity of that. So let us assume in some application you don't need too much security. Okay, so you can accordingly you can design the systems like I need less security in one system, maybe higher security in another system. So accordingly you can design it, you can scale it. Okay, so that's one of the things which is really very important. Of course, it is on the local point, like where the accessible to the human. Definitely, if there is some problem, definitely you can maintain them, and the reliability, of course, the maintaining the reliability of individual sensor node of a smaller node may be easier than the bigger systems. Okay, so these are some of the benefit of Edge AI. Considering this Edge AI benefits, let us move ahead. Okay, about some real data, some threats as of now, how much threats we have received, and we need to understand why security of the hardware is really very important. So if you see these statistics, there are a lot of different kind of attack and threats, okay, and they keep on increasing day by day. If they are keep on increasing, maintaining the security becomes a severe concern or prime concern. Okay, so if we got sufficient motivation behind, like why security is important, let us deep down into the security and try to understand how to maintain the security. Okay. Yeah, so before that, because we are the circuit guy or circuit and system guy, definitely we need to talk about the resilience, security, and the reliability concern. Okay, if you talk about the circuit and system resiliency, there are two major components. One component is the reliability, and the second component is the security. I was talking about one term. If you have very reliable system, okay, or unreliable system in other way, you can get better security primitives. How you can get it, I will explain it later on. But before that, we need to understand there are two major things. Like if you want to maintain the resiliency of any circuit and system, definitely maintaining the reliability and the maintaining security is important. Okay, so let us talk about what these three things are. Okay, three edges are, and how they are important, especially on reliability and the security side. If we talk about there are three things. One is the integrity, second one is the availability, and the third corner is the confidentiality. So they are the three edges of circuit and system resiliency. If you talk about the integrity, there are few things like internal interference, process variations, and the environmental noises. So if the effect of these things are available in the circuit and system, there is a question mark on the integrity of your system. Okay, and these are related to the reliability. If your system is not reliable enough, if your system is not reliable enough, and there is impact of the interference noises or external noise, it is it is creating a problem in terms of the reliability. Okay. Similarly, if you talk about the availability, there could be some kind of faults. It could be the transient fault, it could be intermediate fault, permanent faults. So this question mark on the availability. Okay. And similarly, if you talk about the integrity, there is one more component like hardware tempering, accelerated aging, fault injections. Like if someone is intentionally injecting some fault in the system, this could be question mark on the security concern. Similarly, accelerated aging means like if we have some NBTI or PBTI effects, might be it can change its performances, and it can also change the performance of system, and might be this question mark on the security. Similarly, tampering means like modifying the circuit without the user's knowledge. This is what you can call it the tampering. So these concerns are related to the security. The yellow part which are highlighted, they are the reliability concern. The red part are related to the security concern. Similarly, if you talk about on the availability side, there could be some denial of service attack, there could be control flow attack, and this comes under the security concern. Okay. One third is the confidentiality, like side channel attack, hardware tampering, and the Trojan insertion. Trojan is basically at the time of design, without the knowledge of user, the designer must have added an additional module without my knowledge. And might be that Trojan can be activated at later stage at particular unique combination. And might be this can fail the system. Okay. So the Trojan is also one of the serious concern, and the proper Trojan detection schemes need to be applied, that need to be detected, so that the designer should not add additional module without my knowledge. So these things are some of the concerns related to the reliability and the security. And considering these kind of concerns are really very important to understand. Okay. So with this motivation, I was talking about, yes, the yellow part is related to the reliability and the red part is related to the security. Now, if I'm talking about the hardware security, that is start from the physical world where we are using it. Okay. So if I'm talking about the hardware security, that simply start from the physical root of trust. Okay. And if I'm talking about physical root of trust, what those concerns are which maintain the security of physical root of trust means like the individual sensor node which we are going to use it, where we are going to maintain the security. Okay. So the physically unclonable function or PUF could be one of the hardware security primitives that can maintain the security of your systems, security of your circuit. How that will maintain the security, I will explain in later slides. The second kind of things could be the true random number generator or TRNGs. These TRNGs are basically utilized in the cryptography applications. If you have some data, if you want to encrypt it, just like the simplest example is like whatever the WhatsApp message you are sending, before sending, the information is being encrypted and it is being transferred, and the receiver used to decrypt it and they can read it. Okay. So in between, the people cannot understand what information you have sent. So this is done with the cryptography process, where you have the plain text, you have some key, and based on the process, you can get some encrypted data that we can call it the ciphertext. And accordingly, they are being transferred through some channel. It could be the wireless or it could be wired channel. And then at the end, they are being received and they're decrypted and they can read the information. So the TRNGs are basically utilized where you want to encrypt the data. So for encryption purpose, definitely the TRNGs are very important. Similarly, let us assume if you have some secret key, which is required for the cryptography applications, definitely you are storing those data somewhere. Okay. And if you are storing those data anywhere, definitely those storage elements need to be secure enough as well. Let us assume you are storing your data anywhere, in any storage medium, and if that memory is not secure enough, that can also create a problem in your secrecy. Okay. So if you want to maintain the security, then whatever the devices you are using, they need to be secure. And wherever you are storing your key, that memory itself must be secure enough. So designing a secure memory or attack resilient memory is also a very important concern, and that need to be considered. So it is not just maintaining the security of network, but maintaining the security at hardware level is really very important. I will explain in more detail about what this physically unclonable function is and how they maintain the security in later slides. Okay. Similarly, once you receive this, once you got the physical root of trust, you need to come up with like secure key generation, because if I'm talking about a true random number generator, true random number generator is basically utilized to encrypt the data. But there must be some source where you are generating this true random, or you are generating this key. So if from the devices you are generating your secret key or the keys, if they are not secure enough, that can also create a question mark. Okay, so the secure key generation may be one of the objective to maintain the security. Similarly, secure key storage, of course, I have already told you, like wherever you are storing the data, they need to be secure enough. Someone is writing. Okay, and there could be secure key execution. Whatever the secure key you got, whatever your secure key you are executing, this must be secure enough. And there are multiple objectives that is really very important. So the next abstraction level is, we understood like what is the TRNG, what is the PUF, what is the secure logic. But to get all these things, definitely there is some process. And maintaining the security at those abstraction level is really very important, that we can call them the secure key generation or storage and everything. Once we got all these things, we will utilize this secure key with the plain text or with the message, whatever I have, and then I can get some ciphertext. Okay, ciphertext is nothing but the encrypted data, whatever the message you have, whatever the key you have. After processing these two things, you will get some the encrypted data, and that data we can call them the ciphertext. Okay. This smallest encryption technique could be the XOR gate. Whatever the data you have, if you are XORing with some logic, definitely you can get some logic. So the smallest encryption technique or the logic that can encrypt the data is the XOR gate. There must be some complex systems as well where the data can be encrypted. But yes, the XOR could be one of the simplest one. Okay, so with this one, once we receive all these things, once we are able to achieve all these kind of security cryptography primitives, definitely we are maintaining all those objectives which we were discussing in the previous slide, like integrity, availability, confidentiality, and all those things. So once we are able to maintain the secrecy, maintain the security, definitely we are I can maintain the data confidentiality, I can maintain the data integrity, I can maintain the data authentication, and I can maintain the entry authentication, means whatever the data I am getting, that authentication is equally important. So this is the complete hierarchy of maintaining the security of data that start from the physical world and that end with the network. Okay, so ultimately you know that if I have to process some data that start from the physical world, maintaining the security at the physical world is important. Once you transfer the information, then network security play a major role. Okay, information security play a major role, because whatever the data you have received, maintaining the security of that information is important. Once you have received that information, you are transferring through some channel, so maintaining the security of that network is also very important. So everywhere you have to maintain the security. It's not only the hardware, it's not only the software. In everywhere, hardware, software, network, channels, everywhere. So this maintaining the security is very important, and that need to be considered. I think if you have any questions, you can ask in between. Yes. That is a physical world. So that is start from the local level, like from the actual devices which you are using. And if you are keep on maintaining the security, that you can achieve the resilience which I was talking about in the previous slide. Okay. Yeah, so we are doing in some of the domain here as well. Yeah, these are some of the things which we are doing here. Okay. Now, if we are talking about the hardware security, there could be some possible threats. What those threats are, how to maintain, how to overcome those threats, I will explain those things. So let us discuss one by one what those hardware-based cyber threats are. Okay, the first that is start from the supply chain attack. Okay, second one could be the hardware trojan and malicious modifications. Third one could be the side channel attack. Fourth one could be the physical tampering in the theft. Next one could be the fireware attack. Next one could be the counterfeit hardware. Next one could be electromagnetic interference in the fault injection and eavesdropping and snooping. These are some of the threats. It is not only these other threats. There could be other threats as well in the hardware in the network. Okay, but they are mostly, like if you talk about hardware trojan, I was talking about hardware trojan is nothing but designer is really very important here. If I am the designer and I am not trustworthy, what I will do at the time of designing, I will add some module without your knowledge, and that module may be activated after 10 years or after 5 years or any particular temperature. It depends like how they have designed. Let us assume my chip should work from 27 degrees centigrade to 50 degrees centigrade, and I have designed a trojan that can enable at 52 degrees centigrade. So what I will do, I will test my chip from 27 to 50 degrees centigrade only, and my system will perfectly work. That trojan is not going to be enabled. But might be if your system is, like activity factor is too high, might be temperature may be rise, and because of that, that trojan will be enabled and your system can fail. This could be one of the reasons like to enable the trojan. Enabling the trojan could be the time as well. Maybe after 3 years of time, your trojan will be enabled. This is what we can call it the aging effect. Based on the aging effect like NBTI, PBTI or SCIs, your trojan can be enabled if there is some accelerated change in the properties of devices. So if device property is being changed because of these reliability concerns like NBTIs, might be your trojan can be enabled. Okay, so detecting the trojan is really a serious concern because only designer knows how that trojan will be enabled. Okay, and even though there may be a lot of parameters to detect it, maybe you must have missed one of the parameters, and maybe that one is one of the parameters that enables your trojan. So this becomes one of the serious concern. So wherever you are designing your chip, the design team should be the trustworthy. Okay, so you people need to maintain the whether people should trust you or not. Okay, so maintain these things. The next concern could be like side channel attack. Whatever the information you have, based on the power analysis, based on the delay analysis, the information can be extracted from externally. So these kind of things we can call them the side channel attack. Definitely physical tampering, like if you are modifying the hardware physically after tampering them, this could be one of the security concern. Similarly, the fireware attack, there could be counterfeit hardware. Yes, counterfeit hardware is really very important. Counterfeit hardware means like, let us assume, ultimately I'm going to discuss this thing in more detail, but yes, let me tell you what these counterfeit ICs are. Let us assume you have ordered some hardware, you have ordered some chip, okay? And that chip you want to use in your system. But what happens? Whatever let us assume I'm using my mobile phone. After 3 years and 4 years, might be my system may fail, and I have to throw my chip, my whole mobile phone in the garbage, electronic waste. But is it necessary that all the chips are failed? No, that is not true. Maybe my mobile phone has 10 chips, and out of 10 chips, only 2 chips are being failed. 8 chips are still working. So what e-waste people used to do, they extract those corrective chips, they clean them, and again they add into the supply chain. Okay, you don't know whether I have received the corrected chip or the fresh chip or the counterfeited chip. And because ultimately these counterfeited chips may have degraded their performances, and if they are being used in the mission applications like space and the defense applications, you was expecting your the system should work for 10 years, but the chip was already used for 5 years, so your system may fail after 5 years. because the lifetime of your chip was only 10 years. Okay, so these kind of things we can call them the counterfeited IC. So detection of those counterfeited ICs or understanding the seriousness about the counterfeited IC supply chain is really very important. How they are being added into the supply chain is really very important. So detection of those things are really serious concern, and that need to be addressed. Similarly, fault injection and all those things. So there are various threads on hardware, and everywhere we need to be like we need to concern. We need to be like we need to think about how we should detect all those things and how we can get the correct chip. Okay. Yeah.
Because of the supply of the other person, or you are trying to just analyze what they are trying to prove by observing what is happening at the supply?
Yes. In side channel attack, there could be various kind of side channel attack. One could be the power based on the power analysis. Second one could be the based on delay analysis. Third one could be like electromagnetic information can also be extracted, like what data is being stored. Accordingly, you can get the information. Let me give you the simplest example. If I'm talking about the power side channel attack, so let us assume I have a memory, okay? And if I'm storing logic 0, it must have a separate power profile. And if I'm storing logic 1, it will have a separate power profile. So let us assume if I have 8-bit data, okay? And let me write somewhere, okay? Instead I should write there, okay? So, but where is the pen? Can I write here? No. Okay, perfect. So let us assume I have 8-bit register, something like this. Here I have 8-bit register, and they are storing like each, like for to store 1 bit, I need 1 bit storage element like SRAM cell. Okay, so let us assume in this 8-bit register, there is a possibility like I can store 0000 to 111111. There are possibilities. If I have 8-bit register, total possibilities are 2 to the power 8. There are total possibilities. Now I'm assuming that if I'm storing logic 0, so in this case, let us assume the memory is dissipating 8 nanowatt power. Just sake of simplicity, I'm just telling you. And if the memory is storing logic 1, it is dissipating 10 nanowatt power. Okay. Now, if my register is storing 0000, everywhere 0 is there. So 8 into 8. Okay. This much of power will be dissipated through the register. If my memory is storing 1111, then 8 into 10, 18 nanowatt will be the power dissipation. So based on this information, you will be able to understand what information is being stored. But there may be possibility, let us assume there are 4 ones and 4 zero. Still you can find, because you know the power profile. Based on that, you can get, okay, there is a possibility only 4 are 1 and 4 are 0. So you can just find the permutation and combination, you can guess the key. So this is what you can call them the power side channel attack. Based on the power analysis, you can get the information. You can extract the data, what is being stored in the memory. So similarly, this I have given the simplest example. The similar thing can happen with the delay analysis as well, because if your memory is not symmetrical, like, so what can happen if you're writing 0, it could be different delay, and writing 1, it could have different delay. And if it is different, so based on the reading and writing information, they can extract the timing, and they can guess, okay, while reading 0, this much of delay I have, while reading 1, I have this much of delay, and based on that, they can guess the information. So this is what we can call them the timing-based side channel attack. Similarly, electromagnetic-based, like if I'm storing some data on a hardware, based on electromagnetic waves, there must be different kind of pulses for 0 and 1, and based on that they can get the information. So yeah, these kind of things are, we can call them the side channel attack. Okay, fine. So once we are ready with this one, I was talking about maintaining the trustworthiness at the design is really very important. Okay, so because the designer is the only one who decides whether I am giving you the correct chip or the wrong chip, trustworthy chip or the wrong chip. If you have any question, you can ask in between, right? So let us assume how the designer starts. Okay, so if I am the designer, I will start from the simple visual code or behavioral modeling or anything like this. Okay, so that start from this one, I will write the RTL will be generated. Then gate level synthesis I can do, or I can generate the gate, and I will get the layout of it. Okay, how it is being done? All these things are being done by the design team. But if I am the designer, I am not trustworthy. Can I generate a good design? No, there could be a question mark on that. Okay, so how the supply chain works? If, let us assume I am a chip vendor and some user wants to have some chip for based on their specifications. Okay, so if I am the user, so what this will do? If I am the chip vendor will ask some of the IP externally, because IP, if it is not necessary that you have to create your own IP all the time. Sometimes the existing IP can be utilized to make your chip. Do you know what is this one? IP means like whatever the existing models you have, if you are going to use the similar kind of things, your time of making your chip will be reduced. Okay, so you can use the existing IP. You will ask the IP vendor to supply those IP, and those designer team will use these IPs to make a complete system. But there could be a question mark. What is the question mark? If the IP vendor from where I'm purchasing the IP, if they are not trustworthy, even though design teams are good, might be your whole system may be questionable. So there must be some vulnerability at the chip vendor side as well, where they are providing the IPs. Okay. Similarly, so yeah, of course, if they are asking the IPs, they are expecting they should receive the trusted IP. If they are not receiving the trusted IP, there could be some problem. Similarly, if we talk about, if I have asked a designer to give me the trusted design, if they are not trustworthy, they will not provide, and if they are trustworthy, definitely they will provide you the trusted design. Okay. Similarly, the foundry play also major role. If the foundry is not trustworthy, like whatever the design I have sent to the foundry, and if at the time of fabrication they have modified it or they have changed it, that's also possible. Okay, so the trustworthiness at the foundry level is equally important, and that need to be maintained. Okay, so if I have sent my design, and if there is trustworthy foundry from where I'm getting my chip being fabricated, and if they are fabricating properly, definitely I can get the correct chip. Otherwise, there could be some malicious chip as well, or there could be some untrusted chips as well. That's possibility. And similarly, once this is done, all these steps are being done. Like foundry used to process this wafer, they used to make the chip, and now the chip is being supplied to the end user. Because ultimately, if I am the end user, I need trusted chip. Okay, so everywhere, like if I have from that start from the user, I'm expecting my chip should be correct, it should be trusted, but there could be some vulnerability that start from the IP side, that can go to the designer side, that can go to the vendor side, that can go to the foundry side. And once this is done, it does not stop here. Once the foundry has given you the chip, there must be some intermediate persons who may be supplying the chips. Might be there could be possibility they add the counterfeit IC in between. Even the foundry has given you the correct chip, might be I am the middle person. I can add, okay, foundry has given 100 chips, good chips. I can get the 10 chip back, and 10 chip I have added the counterfeited one. So there's also a problem. Okay, so detection or the security, maintaining the security at each abstraction level is equally important. Okay. As of now, no, but that's possible. So what will happen if Foundry will do these kind of things? No one is going to send their design for fabrication, so their whole investment will be gone. So they are not going to do that. But I just want to say there must be possibility. They can do it. Okay. Yeah. Hmm. Yes, there are many techniques. You can detect them. There are, maybe I can explain, I can discuss in later slides. What are the way to detect the counterfeited IC? So I will tell you, I will explain this thing in more detail. Any other questions? Any questions from the online? Okay. So it is, I don't know whether it is interesting or not. If you have any concern, definitely you can ask the things. Okay. But I think now you are in fear, right? Huh? Okay, what is going to happen? Okay. Perfect. So let us move ahead. So okay. Yes, this is also very important. I think he was talking about yesterday something like how to maintain the trust and security. So why it is happening? Whatever the things which we have discussed here, there could be the possibility, the possible, the vulnerabilities at the IP side, it could be at the design side, or it could be at the vendor side or foundry side. Why it is happening? What are the reasons? The reason is, it is not necessary that everything is happening at the same place. Because if we talk about the complete supply chain or complete process of chip manufacturing, designer team must be sitting in the in let us say in India. I have sent the design for testing purpose somewhere else. The GDS has been sent for like fabrication at somewhere else, like in other foundries. Packaging must be done somewhere else. So there are a lot of process, like to get the complete chip, the designer, then fabrication, raw wafer I will get, then maybe dicing, maybe packaging, and then maybe testing. So there are n number of process to get the correct chip, but all this process is not possible to complete at the single place. If we are doing at the different places, let me explain over here. Let us assume I'm designer. Let us assume I am here. I am the designer. I'm asking. I can ask IP from here. I can ask IP from here. I can ask IP from here. There must be various locations where the IPs has been generated, and for my design, I can ask the IP from anywhere. If let us assume if I'm asking the IP from 10 locations, and out of 10, one location is not trustworthy, that can create a problem in your whole system. Okay, so because the whole supply chain does not can be completed at a single place, the designing can be done at different place. After GDS, you are sending the design for the fabrication to the some foundries. After that, you are sending somewhere here and to fabricate it. Might be assembling, packaging, testing is done at different places. So because there are many things are involved, okay, many locations are involved, so maintaining the security everywhere may be a tricky job, may be a difficult job. And if any one place is not performing their task properly, they are creating some problem in the security, the whole system may fail. Okay, so and this is why the security becomes a serious concern. Anyone can add the Trojan. Any of the designer can add the Trojan. If I'm using the untrusted foundries, that can also create a problem. That could be one. Designer is also one of the important things that play a major role. If I'm not the good designer, I'm not trustworthy, definitely I can add some module which can be enabled at a stage. That we can call them the Trojan. Okay. Similarly, IP piracy, IC piracy, counterfeited ICs. So there are various things which are really very important, and they create a question mark on the hardware security. So with this fear, with this kind of motivation, let us move ahead. Okay. Yes, one more thing is left. Let us assume I have sent my design for the fabrication. Okay. As of now, I'm telling you all the problems. Okay. I will also tell you the solutions. Don't worry. Okay. So it's not like there is always a problem. There is a solution for each problem. Okay. How to do that, how to detect those things, I will explain. If I'm talking about the supply chain that starts from the design, okay. So let us assume what is happening. Okay. So if I'm the designer, okay, the cloned design can be utilized. This could be one of the possible. So if we talk about the supply chain vulnerabilities, that can start from the design, that can go to the fabrication, where let us assume I have sent my design for the fabrication and the foundry has overproduced. I have ordered them to fabricate 100 chips, but they have fabricated 110 chips, and they have given back only 100 chips, and now they can use those 110 chips to aid into the supply chain without my knowledge, and they can earn more money out of it. That's a possibility. Okay, so at the fabrication level, that's possible. Like overproduction, out of spec production, like production of the design may also be possible. Okay, and defective chips fabrication may be possible. Tempered chip, tempering of the chip may also be possible. Similarly, if you talk about the assembling, there could be some possibilities like overproduction, defect, and everything. Similarly, at the time of distribution is major concern, especially on the counterfeited one. Let us assume my chip is being fabricated. It is done. It is already fabricated. Now, the foundry will not supply to the user. There must be some vendor who used to supply the chips. Okay, and if I can aid in between the counterfeited IC, that's question mark. Okay, so all the maximum counterfeiting is the possibility of maximum counterfeiting is at the time of distribution. The distributor is the major source of the counterfeited IC. Okay, and then once I was talking about if I have thrown my electronic waste, then someone may process it, they can recycle it, and they can aid into the supply chain. This is also one of the concerns which I was talking about. And yeah, so it's like the understanding the seriousness of the electronic waste is really very important. We keep on using electronic gadgets, but after using, we are throwing it without knowing where my device is going to be used after I throw it to the electronic waste. So that is really very important. You should be serious. You should be careful before throwing your mobile phone in the garbage. Okay. There is one very good paper especially on the SRAM or especially on the RAM. What that paper says? That paper says that ideally the characteristics of SRAM is once you power off the device, your data is vanished. Okay, you lost the data. But this is not true. In some sense, because ultimately these designs or these circuits are being made with the help of transistors. If they are made with the help of transistors, there must be some capacitive effects. And might be some charge can be stored even though you have powered off. Okay, and based on that charge storage, might be some data can be stored. This is really very important paper. You can go through it. Might be I can read the title. The title it is something like be aware of throwing your SRAM in garbage, something like that. You can search with this keyword, you will get it. So that paper gives you the information about. It is not like I know conceptually I have read like the SRAM data is vanished after the power off. But might be there is some inherent property of the devices that can store in the form of charge, they can store some data. And if they can store some data, the information can be extracted back. Okay, so that's also one of the concern, one of the seriousness. Okay, so After this much of fear, let us come up with the solutions. What is the solution of those problems? Okay, so there are some solutions too. The solutions are some secure boot is important. Yeah, this is at the booting level. Hardware security modules need to be added into the chips. This is really very important. Okay, so hardware security modules is important. Physically unclonable function becomes one of the major component if you want to maintain the security of your systems. So what this physically unclonable function is, I will tell you, and this becomes one of very important thing to maintain the security of your devices. And then fireware integrity verification, then hardware based root of trust. Similarly, threat and attack mitigation schemes need to be applied. There could be some temper resistant packaging and sensors, and there could be some hardware metering. Hardware metering says that, let us assume I have asked the foundry to fabricate 100 chips. Okay, there must be some metering kind of scheme. If I have asked them 100, they can fabricate only 100. So not more than that. So this kind of scheme, we can call them the hardware metering that prevent from the overproduction. Okay, so the hardware metering prevent from the overproduction. Okay, so there are some of the security measures that can be considered. Yes, so with this one, let us start with the cryptography. बोल तो नहीं हो रहे आप लोग? Yeah? Yes.
You said about the foundry can take my chips basically and sell it in the market. I can understand about the simple chips that they can reverse engineer.
Yeah.
And then they will know what it is and they will go to appropriate vendor and sell my chips.
Yeah.
But if you talk about the processors and all, which is the biggest market in the field of the VLS side, has billions of transistors. It's almost impossible for them to reverse engineer everything.
So the only process is not important. Major threat comes at the lower level, which is the sensor level. If you are using some IoT nodes and they are being tempered, they are being cloned, your information, most of the information, wherever you are collecting, where you are collecting the data, at the lower level, at the sensor side. And if they are tempered, if they are vulnerable, your information can be transferred somewhere here and there, even though before processing the things. So only the processor is not important. Maintaining the security of lower node which you are using at the ground is major. Like they are more vulnerable to the attack. They are more vulnerable to the security concern, not the processor. Processor is just whatever information you are getting, they are used to process it. But if I have received some data, if they have manipulated it, processor will process the manipulated data only. They don't care about what data I am getting, whether it is manipulated one or the correct one. So the major concern is at the lower side where the actual data is being collected. So that's important. Okay, so T is there. What is the status of T? Okay, fine. So otherwise they will start sleeping, right? बस सोने तो नहीं दूंगा मैं, ये सवाल पूछूंगा आप लोगों से. Okay, fine. So let us talk about the cryptography. I was talking about some of the hardware security primitives, and that hardware security primitives are the physically unclonable function. There could be the TRNGs, there could be the hardware Trojan, and many things like counterfeited ICs. These all are the hardware security primitives. Okay. If you want to secure the information, secure the data, whatever you are transferring through the untrusted channel, definitely you need to encrypt them. Okay. So if I have some plain text here, and if I want to secure it, because ultimately it is not necessary the sender and the receiver both are very close to each other. They are being transferred through some channel, some medium. This medium could be the wireless medium or it could be some wired medium. Even though it is wireless or it is wired, before sending the information, they must be secure. They must be encrypted. Okay. So what this says, the cryptography says that whatever the plain text you have to encrypt them. Okay. There are different encryption mechanism, encryption algorithm. Okay. And they use the secret key, and this secret key are being generated from the true random number generator. Okay. So if you talk about the VLSI perspective, definitely The designing true random number generator is one of the research domain where you can work on. You can generate the true random number by utilizing the process variations and other things. This is what I was talking about. Let us assume I want to generate a random number. Okay, how it could be done? The simplest thing is, I know that the process variation of any device is completely random in nature. You cannot predict them. Okay, so if there is more process variation, more randomness is there, and more random key can be generated. So this is how you can connect it. Let me say it again what I'm saying. Let us talk about what is the reliability. Reliability says that whatever the circuit I am making or whatever devices I am making, they must be robust enough even though there is some change in environmental conditions. There is some change in the parameter. Maybe process variation, if I'm changing the supply voltage, the performance should be maintained. If I'm changing the temperature, it should maintain the similar kind of performances. This is what I'm saying, the circuit is reliable or the system is reliable or the device is reliable. But with the technology scaled down, maintaining the reliability becomes a serious concern. At the lower technologies, once you fabricate the chip, you cannot achieve the similar kind of reliability with the older, as compared to the older technology. In older technology, the effect of PBT variations or process variations are very less, whereas at lower technology, they are very high. If they are very high, means more randomness comes into the picture. And if you have more randomness, you can utilize this randomness as a benefit to generate the random number generator. So this is what we can call it the Abda Meowser. Okay, so you have unreliable device, you have unreliable circuit, you can utilize them to generate a random number. That can be utilized for the cryptography application for the encryption purpose or decryption purpose. Okay, so this is what my team is doing. Someone is doing designing the circuit. If that is unreliable, that can be utilized to make a secure system, and the vice versa. Okay, so yeah, be seated and ask. Don't worry. Yeah, because the similar kind of, yeah, so yes, very good question. The single true number generator where you have generated the key, that key will be used for the encryption, and the same key will be transferred through the receiver as well. So it's not like you have a different kind of the key generator in two devices. No, a single key, whatever the key you have generated, that will be used by the sender as well as the receiver. The same key will be used. So they will be transferred. Like with a plain text, the key will also be there. So there are various algorithms that can generate the secret key. It's not about the variability. There, with the help of algorithms, it can also be generated. That we can call it the pseudo random number generator. Okay, so with the pseudo random number generator, the similar algorithm will be used by the sender, by the receiver, and they can get the key, and they can use for the crypto encryption and the decryption purpose.
Sir, how can we design two random number generators with different mechanism? Let's say using the phase noise of the oscillator, and the second one with the, let's say, LFSR, like shift register. How do you actually compare the quality of two random number generators? How do you say that this is the best that I can do?
In reality, nothing is true. So you can call them the random number. But yes, if the repetition of those key generated key is less, then you can call them, they are very close to the true random number generator. Based on their property, what either you are using the inherent property variability or you are using the LFSR and all those things to generate the key, they have different kind of repetition pattern. And based on that, you can decide, okay, they are truly in random, or they are close to random, or they are pseudo random. So this depends like complexity, because if you are using the 64-bit and you are tapping at many places, you are XORing them, might be you can get more true output. But it depends where you are tapping, what is the complexity of your LFSR. So that decides. Yes. Yes. So they will use a similar kind of, I was just he asked like LFSR, if I'm using LFSR to generate a key for the sender, similar kind of LFSR will be used at the receiver end. So they will get the same key because they have the same hardware. This is the network security concern. So it's not, still they are using they will use a similar kind of algorithm because they know like what kind of algorithm are being used to generate the secret key at the sender. Similarly, they will use, so at the time of encryption, what kind of algorithm they have used at the receiver, they will use the similar kind of things. So this is what we can call the compatibility. They are compatible, that is why you are able to see it. If let us assume I am sending my email from Gmail to let us assume the Rediff mail, if they are not compatible, they will not receive the message. They will get XYZ delta, something like that. Okay. Once they are compatible, they are able to decrypt it, you can see the actual message. That's possible. There's always a possibility. Vulnerabilities are everywhere. You cannot say whatever the key you have generated is 100% secure. So I was talking, I think at the beginning, I told you, the key can be stored somewhere. And if that memory itself is not secure, then you cannot say the key which I have generated is random, but I have stored in unauthorized places or unsecure places that can be accessed. That's also one of the possibility. So, okay, so this was the similar process is adopted at the decryption or the reverse process is adopted, and I can get the plain text. Okay, so now, I think we can take a break. We can have a tea, and then we'll come back, and I will tell you how your puff works and how to authenticate the chips. Okay, so let us take a short break of 20 minutes, and then we'll come back and we'll continue. Hello. Okay, so recording चालू है ना? Okay, perfect. So I think we were discussing about decryptography systems, where we talked about the data can be encrypted with the help of the secret key, and that secret key can be generated from the TRNGs, true random number generators. And the true random number generators are utilizing the inherent process variations of devices, and based on those variations, you can get the different key from the different set of circuits, and accordingly you can say, okay, they are the random in nature. The similar kind of concept can be utilized, especially if you want to authenticate your circuit or authenticate your chip. So here I just wanted to tell you, like, whatever the edge devices or any sensor nodes you have, if you want to authenticate them, if you want to maintain the security of those things, one of the security primitives are really very important, and that we can call them the physically unclonable function. The physically unclonable function is nothing but they are just like a biometric of a human, like just like if I want to identify myself, my biometric, like everyone has a unique biometric, right? The similar kind of things are used in the puffs as well, because each variation, like each device has the different variations, and if they have the different variations, the key that can be generated for a same set of challenge, it can be different. So the challenge response pair of the circuit or any edge device will be different. So the puffs are nothing but they are basically utilized to authenticate the chip, authenticate the circuit, or authenticate the AGI node, whatever we are talking about, and they are different for each one of the devices. So, but the question is how they works. Okay, so basically, if you want to authenticate the things, authenticate the AGI chips, there are two ways. The first way, by utilizing the public key, and once you have the key, you can encrypt them, you can decrypt them, whatever I was talking about in the previous one. But what is the challenge? What is the problem with that one? So actually the key is being stored in the server, okay, in the public server. This key can be used by the AGI chips, by the edge devices, and those key can be used to encrypt or decrypt the information. But what is the problem here? They are getting the key from here, and again they are storing the data here only. Okay, but the actual problem is because the key is publicly available. If the attacker knows which kind of encryption technique you have used to encrypt the data, they can simply get the data and they can encrypt or they can decrypt it directly. So this is a problem with the available public key cryptography systems. So to overcome that problem, we have to utilize some modules or something that inherent property can be utilized to generate the key so that the public key cannot be used. And if I am not using the public key, definitely the security will be better. Okay, so let us assume if let me give you the simple analogy. Let us assume someone wants to identify like myself from my card, like my iCard. So if you have my iCard, you can say, okay, this is you, and you can be identified myself. Similarly, but you cannot break my hand, right? You cannot, of course, that is also possible. But the identifying from the biometric can give you the surety, okay, I was physically present there. Okay, the similar thing happens with the public key and the actual key generated from the edge devices. So the public key is there, but there are some problems like a separate memory is required to store those keys. Okay, they are bulky, they are heavy in nature, and similarly, they can easily be copied or they can be cloned. So this is the problem, especially if we are doing the cryptography with the public key. Now, if I'm talking about the private one, like the generating the key itself from the same devices, same edge devices, how that's possible? That is possible just like the inherent process variations. So I was talking about these things before. Let me repeat it again what I was saying. If you scale down the devices, with the scaling down, the effect of process variations are more. If the effect of process variations are more, what it means that they will have more variability than the existing techniques or the older technologies. This is the problem, especially if you are talking about the reliability. But this problem can be utilized as a benefit, especially if you are talking about the security. So reliability and security here are like there is a race between if it is good, like if it is secure or it is unreliable, the system can be secure and the vice versa. Okay, so the inherent variations are being in the devices are being used to generate the key for the cryptography purpose. So they and how that is done? Basically, there is a separate module in the chip. That separate module, we can call them the physically unclonable function, and those physically unclonable functions generate the challenge response pair based on their variations. So let us assume if I have two devices will have a different kind of variations. If they will have a different variations, even though I have applied the same challenge to both the devices, I will not get the same response because they have the different variations. Okay, so this is how the challenge response pair is different for different chip, and this becomes uniqueness. This becomes a unique property of any devices that gives you the identification of those devices. Okay, so to really authenticate those devices, puff becomes an important component at the time of design. So you have to add one module that we can call them the puff. There is challenge response pair. You are generating the responses based on the particular challenge. Okay, and because they are using inherent property process variation properties, there is no public key involved here, so the security is better as compared to the public key cryptography. Okay, so the good thing is like no public key storage in the server. Okay, and encryption is done through individual like inherent property of the process variation. There is a separate module that we can call them the puff, and the benefits are we do not need to store the key because we are generating from its variations. No like public key cryptography is required because they are generating the key from themselves only, and cannot be cloned or copied because for each device the puff will have a different property, so it cannot be copied. It is nothing but it is not, they are utilizing the process variations to generate those keys. Okay, and similarly, yeah, they are utilizing the nanoscale variations, and they are more they are giving good challenge response pair, especially if you have more variations. Okay, yeah.
So if I fabricate, let's say 10,000 number of chips, I agree that the variation will be a lot at smaller technology nodes. So if I plot the histogram, then I will see the variance of the Gaussian distribution will be higher.
Yes, yes.
But there is a central part where most of the devices will lie in the typical corner, so they will be identical, right? So their PUFs will also be same.
Yeah, so absolutely correct. But what is happening here? Let us assume I have designed, let us assume 10 chips. Okay, in the first chip, the threshold, let us assume I am using the SRAM as an authentication purpose. So let us assume there are 6 transistors. Okay, in 6 transistors, there is a possibility one transistor may be at higher threshold voltage, maybe threshold voltage can increase, one transistor threshold voltage can reduce, one can have the typical, but it is not necessary the transistor of like threshold voltage of one transistor is increased, but with what amount it has been increased. So there is a huge variation. So there are 6 transistors. There is a 3 possible changes: low, high, and the typical. And even though in low and high, there could be how much low, how much high. So there is a huge variation. Of course, I do agree. If you plot them, like there could be some histogram kind of characteristic where most of the things will be centered around, but they will be scattered. So if I have 100 chips, the performance of one chip will lie on the left side, second chip will maybe right side, someone will here and there, but they will not be identical enough. Even though the probabilities are more, but they will be scattered. So they are utilizing those scattered property because you have 6 transistors. In the 6 transistor, 3 possible variations. In the 3 possible variation, percentage of variation is also important. Okay, so you have a lot of permutation and combination. Okay, so that's important. Okay, so you have these kind of benefits you can achieve out of this one, like which is the puff devices. So let us see how this puff works and what are the different architectures of puff designing and how we can generate the responses after applying the challenges. Yeah. 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 Anything different, yeah. Mm-hmm. Yes, of course. So there are a lot of possibilities. Like you have 6 transistors, 3 corners, percentage of variation is also important. So if you multiply, you will get millions of combinations that is possible to generate a key. And this is what you are getting, the variations.
But like if we do transistor level, for module level, so how can I?
So module becomes you have to design the module by transistors only, na? So ultimately that becomes the part of that one.
I'm saying if I want make a puff at the module level, So like transistors are all remain all the in my design transistors are all same. There is no variation such variation. But if I have to add some module like designing of any like adder subtractor anything, so how can I make the puff in that way?
No, it's not like that. So let us assume puff. So where you will use the adder? You don't have to fabricate the adder chip. No? Adder is the part of your chip. Okay. So let me say it in other way. Let us assume you have designed a processor or any sensor node where what will be the sensor node? You will have a sensor that can sense a particular parameter. Then there will be amplifier. There will be some ADC. ADC will be there. Then there must be some storage element. So this is a typical block that you can think of for a sensor node. Okay. Now your sensor node is done. Now you want to make like how unique your this sensor node is from other one. So you will add one additional module that we can call it the puff. And puff can be designed either with the help of ring oscillator, arbiter one, SRAM. There are many ways to design the puff. So it is not like the puff, whatever the key you are generating, that will be generated from the adder, whatever you are talking about. There is a separate module for the puff. This is added into the chip, and they work as identification purpose. You got it? Yes, so we intentionally create some variations on that at the time of fabrication so that you can get the unique responses for a particular challenge. Okay, so let us talk about how this puff works, how they authenticate the chip, and how you can design your own puff. Okay, so let us talk about, yeah, I think this is already I have told you. There is no storage key, no public cryptography, cannot be cloned. They are using the nanoscale variations, which I have already told in the previous slide. Now let us talk about the concept of the physically unclonable function. I'm taking just like a classroom, right? It's not like a workshop. I'm considering you are a student. Okay, of course you all are. Some are faculty members, so sorry for that. Okay, I'm teaching like a student. Okay, so let us try to understand how your puff works and how you can generate or how you can validate whether the key is correct or not. Okay, so let us try to see. Here is my authentic chip. Let us assume, I am assuming that it is the authentic chip A. In this authentic chip, you are like, if I am supplying through a untrusted supply chain, then there is a possibility of the cloning, there is a possibility of counterfeited supply. So to avoid that, what I can do? If I want to validate it after passing through an untrusted supply chain, whether the chip which I have received is a trusted one or not, there is a question mark on that. You cannot say after passing through a supply chain without checking it, you cannot say I have received the authentic chip. Okay, so whether the chip which I have received, that is a trusted chip or not, there is a question mark on the authentication purpose. So how to do that? So for that purpose, what I will do at the time of designing, I will add one module like a puff that acts as a biometric of your chip. Okay, so one module, puff module are being added into the actual design, actual chip which you want to fabricate. And then what you have to do at the time of design, you have to create a challenge response pair. Because what is the challenge response pair? Challenge is nothing but the set of input which you are providing. Based on the input variation or inherent variation, it will give you some response patterns. Okay, so you have to create a challenge response pair. You will provide some challenge that will give you some response. You have to create a challenge response pair, and that will be the database for the chip, whatever you have here. Now, once I have designed it, I will send to the untrusted supply chain. Now, what will happen? Once this is passed through this one, once I have received the chip, I will apply the same challenge. And if I am getting the same response which is in the database, I can say I have received the trusted IC, because the challenge response pair is unique for each puff. If it is unique, it means that if I am providing this challenge, I should get this response in this chip as well. If I am not getting the same response, it means that the chip is not authentic. Okay, so for that purpose, what I will do, I will compare this challenge. I will pass the same challenge to this this chip, and then I will try to authenticate. I will try to generate the responses, and I will compare this response with this response. And if they are same, my chip is authentic. Otherwise, it is not authentic. So this is how a simple, typical, physically unclonable function works. Okay. So basically, if you have any question, you can ask how you are getting this puff, how you are getting this challenge response pair. So basically, this set of challenge response pair at the time of designing, after passing through the supply chain, you have to compare them. If they are matching, you can validate, okay, I have received the authentic chip. If they are not matching, it means that the chip which I have received is the untrusted one. I will tell the vendor, okay, please provide the correct chip. Okay, so this is how the puff works. Now, the simple thing is like I was talking about, even though I have used the same circuitry in all the designs, but because all the chip will have a different variations, different kind of process variations, even though I will provide the same challenge, I will not get the same responses. Responses will be different for each chip because they have a separate process variation. They have a different process variation. Because of difference in the process variation, the responses will be different. So the challenge response pair for each chip which you are fabricating, even with by utilizing the same puff, will be different. They will be different. Responses will be different. So the CRP which you are generating, that will be different for each physically unclonable function. Okay. So that's really very important. And this is basically utilized because we have the database of challenge response pair. If the challenge and response pair is matching, if you see here, challenge and response is matching, I can say it is a authentic IC. And if the challenge and responses are, like challenge response pairs are not matching, you can say I have received the counterfeited IC. I will request for the correct chip or authentic chip. Very good question. I am going to explain this thing. Don't worry. In the next slide. Okay. So, so this is how the challenge response pair works. As of now, what we have considered? We have considered that there is no effect of there is no effect of temperature variation, there is no effect of the voltage variation or supply voltage variations. But if I am trying to design the circuit, we know that most of the circuits are affected by supply and the temperature variations. If they are affected by these things, how they are impacting on the challenge response pair? This is really very important. So let us try to understand what is the importance of supply in the temperature variations, especially at the time of the puff designing, and how we should validate what is the margin where the variation in temperature or variation in supply voltage is acceptable. Okay, there must be some range where it is acceptable. Beyond that, it is not acceptable. Okay, so we have to find what is the range where the temperature or anything can be acceptable to get a similar kind of challenge and response pairs. Okay. Any questions at this point? Anyone? बोर तो नहीं हो रहे आप लोग? हैं? किसको इसको नींद आ रही है? समोसा खा लिया आप लोगों ने ऐसे? चलिए. Okay. So let us move ahead. Let us try to design a typical physically unclonable function. Yeah, there are some properties. Let's talk about. To understand the puff, there are some properties which are really very important that need to be calculated, that need to be evaluated, and those properties are like the uniqueness, reliability, reproducibility, unpredictability, temper resistance, or realizable, and there are many things, like there are many properties. We will discuss one by one what is the meaning of this one. Major property in the puff evaluation is the uniqueness, reliability, and then key error rate, bit error rate. These are some of the properties which are really very which are important to evaluate. I will explain these parameters later on and how it could be calculated. Maybe I can discuss that as well, maybe in the next lecture. But what is the importance? The important things are this one. If I am designing the puff, these things are very, very important. If I am designing a circuit, if I am designing a puff, maintaining the reliability is important. But someone may ask one thing. Just now I told, if my chip is unreliable, I can get good puff. But here I am saying reliability should be high. There is a contradictory statement here. Okay? So here the meaning of reliability is a bit different. What is the difference? Let me explain. I am talking about if there is some internal variation or inherent variations, I am based on that challenge, I am getting some responses. Here the meaning of reliability is, it does not mean there is no process variation. It means that even though I am applying the same challenge with different environmental condition, I should get same response. This is what the meaning of response is. Meaning of reliability is. Let me say it again what I am saying here. The general meaning of reliability is there should be less process variation. This is what as of now we have understood. Okay? So higher reliability means less process variation. This is what we know. But in terms of physically unclonable function for the puff design, this reliability's definition is little bit different. How that is different? It simply says that it will use the process variation to generate the key based on the challenges. Based on the challenges, it will generate the responses. But if I change the temperature and applying the same challenge, it should give the same response. If it is giving the same response within the environmental variation, supply variation, considering the process variation, then I can tell them it is a reliable puff. Are you able to differentiate these two terms? They are a little bit confusing, but yes, you have to understand what I'm saying. If you are still in doubt, ask me, I will answer again.
The variation across the chips that you want, but one chip, when it's fabricated, it's even if the temperature environment changes, the PU should not change.
Yes. So I am utilizing the process variation to generate the responses, and once fabricated, the effect of environmental variation should be less.
Yes.
And that is defining the reliability of that thing. Okay, so that's important. Yes.
Providing a challenge, there is a challenge response pair.
Yeah.
So that means, and for a particular challenge, it is mapping to a particular response.
Yes.
So there has to be a mathematical function that is governing this property.
Yeah. So because they are utilizing the inherent variations, so they are, yeah, of course. So there must be some correlation. Like if I am giving the 0, 0, 0, 0, I am getting this response. If I will give 0, 0, 0, 1, then I am getting some response. So the property of puff is it should not be predictable. It's not like if I am giving 0, 0, 0, 0, I am getting this response. And if again I am giving 0, 0, 0, 1, so I am getting this response. So I can relate, okay, if I am increasing 1 bit, I am getting the response 1 bit increment. So it should not be like that. It should not be predictable. It should be one way kind of. So if I am giving some challenge, let us say for 0, 0, 0, if I am getting 1, 1, 1, 1. For 0, 0, 0, 1, I am getting 1, 0, 1, 0, 1, 0. So there is no correlation between these two.
That might be one to one. There is a function governing this property, and if it is a function, mathematical function.
No. But what we are doing? No. You are giving the challenge. You are getting response based on the variations. Now you are clubbing them. You are getting the CRP. That's it. Okay. Again, you are giving the challenge. You are getting some response. We are clubbing them. You are getting the CRP. You know if there is 8-bit challenge, 8-bit response, there will be total 16 bit. The first 8-bit are challenge, last 8-bit are response. You know the CRP now. So this is how it works. It is not necessary. One more thing, that it is not necessary the number of bits in the challenge is same as the number of response bits. It depends on the architecture. Okay, even though you have 8-bit challenge, might be there is a 2-bit response or 1-bit response or even more than that. Okay, so it is not necessary the number of bits in the challenge is remains same as the number of bits in the responses. It completely depends on which kind of architecture you are going to use it. I am going to show you few of the architecture where you can change the number of responses. Okay, so I am going to discuss those things as well. I don't know how much informative it is, but yes, it is. For me, it is, right? It is. Okay, so I was talking about this reliability. proven reliability, where I should talk about the voltage fluctuation. There should be less effect of the voltage variation. There should be less effect of temperature variation, and there should be less effect of the aging effect. Aging effect I was talking about at the beginning. I told you NBTI, PBTI, SCIs are one of the temporal degradations. With the time, their effect increases, and might be they can change the performance of your devices and ultimately systems. Okay, so the effect of PBT variations should be as small as possible. I am going to discuss the impact which you ask, like how they are going to change if something is changing. So that will be explained in the next slide. So if I am designing a chip, there should be aging resilient, there should be process temperature variation tolerant, voltage fluctuation tolerant. Okay, the second thing is like flexibility and portability. Of course, there should be small area. It's not like I have 1 millimeter by 1 millimeter my actual chip, and you are using 2 millimeter by 2 millimeter for the PUF designing. Is this good design? No. It is requiring more area than your actual design. So this is not acceptable at all. So the area is a major concern. And if you have used a more complex PUF, that will require more power to operate it. So this is also one of the concerns, because this is additional hardware which you are adding into the chip. If you are adding additional hardware, might be that will require more power. So this is also one of the penalty in terms of power. So you should design your PUF in such a way that should dissipate minimum power, so that there should be no power overhead in overall chip. Similarly for the area, similarly for the technology, like what technology we are using, that important, like I told you, for different technologies, their inherent variability will be different. Similarly, if you talk about, yes, this is very important term, uniqueness of the responses. Each PUF must give you the unique responses. If they are giving the same responses, like my biometric cannot be same like your biometric. If this is same, it's a problem then. Then Aadhaar sabka ek jaise ho jayega. That's the problem. Okay. So the uniqueness should, like the response should be unique for each physically unclonable function. Now, if you talk about the security, there should be resistance to attack. There should be no possibility to side channel attack, so that I can guess the information what key is or what responses are. If someone is able to guess the responses for a particular challenge, this is a problem. Okay, so this must be the side channel attack resilient as well, and that is very important. And one last parameter is the entropy source. Ultimately, source of entropy is like variability should be very high, so that you can get the better challenge response pairs. So there are some of the properties, some of the features which are required at the time of PUF designing. Okay, at the time of PUF designing, these many features are needed. They need to be considered. Once we know all these fundamentals, let us try to design a basic physically unclonable function. Okay, the first basic unclonable function that can be designed. Before that, let us talk about the taxonomy. There are various kind of, this is the smallest or simplest taxonomy, but there is a broad one. I have not kept that one. I have that one, but maybe I can share you some papers if you like, of detailed PUF taxonomy, where there are more than 20 classifications, way of classifying it. But as of now, I have considered only 2, intrinsic, extrinsic, and ultimately we are going to consider these 2. Delay based, where arbiter PUF and the ring oscillator PUF will be used. Okay, one thing we can consider, this SRAM based PUF I will talk about, how this SRAM can be utilized to design the physically unclonable function. So SRAM based PUF I can also explain. So, but let us talk about what this RO PUF is, how you can design this RO PUF, and how you generate the challenge and response pair, how you can make them resilient to the aging effect, or resilient to supply in the temperature variations. Okay, so let us see. ठीक है, आगे बढ़े. Shall we go ahead? Okay. I was talking about, let us talk about the RO based physically unclonable function design. Okay. Yes, this is the simplest version of the RO based PUF design. How this works? Don't write anything, let me explain it. You will understand everything. Okay. फिर घर पे बैठ बना सकते, you can make at home. Just try to understand what is happening here. Here I have the ring oscillators. We know that what ring oscillator is. If the chain of inverter is connected and they are feedback, then they form a ring oscillator and they will operate at certain frequency that depends on what is the delay of individual inverter and how many stages we have. Okay, and that decides what is the delay or what is the frequency of your ring oscillator. So simplest version of ring oscillator is just by connecting the simple CMOS inverter in an odd number of CMOS inverter in a chain, and they can form a loop, and that will give you some frequency. Okay, so let us assume I have n number of RO puffs. There is 2 multiplexers. Okay, how that works, let me tell you. Let us assume I have 2 multiplexer of some order. Let us consider the order of this multiplexer, like there are, let us assume 4 control signal in each. Okay, so considering I have a 4-bit challenge here. Okay, if I have a 4-bit challenge over here, and this 4-bit is given to this multiplexer, and again 4-bit is given to this challenges. There is a catch. What is the catch? Let me tell you. There are 2 things. If I am using the same challenge as a control signal for both the multiplexer, what it means, if I have a 0, 0, 0, 0, the first input will be selected here and the same input will be selected here. Is this possible? So let me tell you like how at the architectural level or at the circuit level or at the design level, you can increase the challenge response pair. If I am using the same challenge to both the multiplexer, the same number of same input will be selected from the both multiplexer. Now let me change it again. If I am using the 4-bit challenge here and a separate or different 4-bit challenge over here, so the total number of challenge will be 8. Okay, so if this is 0, 0 and this is 0, 0, 0, 1, so the first will be selected here and the second will be selected from here. Is this possible or not? So the challenge response pair depends how you are configuring your multiplexer. Even with the same design, you can increase the challenge response pair by 2 times just by changing the challenges or input or control signals of both the multiplexers. Okay, so let us assume, for sake of simplicity, I am considering the same challenge for both the multiplexers. Okay, both the multiplexer. So let us assume I have given some input like 0, 0, 0. The first, so whatever the output of the first ring oscillator is, that will be transferred to this counter. And similarly, whatever the input of the, like whatever the first one is here, the similar will be transferred to here as well. So let us assume it is a 4 input. So there will be 16 RO on the upper one. Okay, so 16 RO will be connected here, and similarly 16 RO will be connected over here. So total number of ring oscillator will be 32. So total 32 ring oscillator will be there. 16 ring oscillator will be connected to the first multiplexer, 16 ring oscillator will be connected to the second ring oscillator. And if I am giving some challenge, let us assume 0, 0, 0, this will be selected, this 17th one will be selected. Okay, from here the first one and here 17th one will be selected, and because they will have inherent variation in the transistors, their frequency will be different. If their frequency will be different, the counter will increment with a different frequency. And if they are incrementing with a different frequency, let us assume this ring oscillator is fast and the 17th one is slower. So this counter will reach to 1, 1, 1 early than the next counter. So here, once this is reached to 1, this will compare any one of the counter reached to 1, they will compare which counter has reached to 1, 1, 1, 1, 1. Accordingly, either they can give the response like 0 or 1. So this 0 and 1 is completely unpredictable, and that depends what is the performance of your ring oscillator is. If I will use a different combination, let us assume 0, 0, 0, 1, then the first one will be selected here and the 18th one will be selected over here. Might be the lower one could be the faster than the upper one. So you will get the different responses. So the challenge response pair completely depends on how much variations you have in the individual ring oscillator, and the individual ring oscillator frequency depends on how much variations are there on individual inverters, and individual inverter can be made of the PMOS and NMOS transistors. They can have the different variations. So you have lots of possibility of variability, and if there's a lot of possibilities, the frequency, the possible range of frequency variation is also very high, and if that is high, you can get the variation in the responses here.
So while making the layout of this circuit, it should not be symmetric now, right?
Yes, if it is unsymmetric, जितना खराब बना लोगे उतना unreliability होगा, उतना बेहतर होगा. That's important. One important catch is here. So if you are perfect in layout designing, you are not good puff designer then. Okay, that's important. Okay, so this is what I told, like how much configurable, how you decide the challenge response pair. So here you can have the 4-bit challenge, and you are getting only 1-bit response all the time. So the total challenge response pairs are, how many challenge response pairs you have? 16 only. Okay, so total challenge response pairs are 16. Now let me break. If I am giving a separate challenge here, separate challenge here, so now my CRP has been increased by 2 times. They become 32, because 8 challenge response pair for first multiplexer and 8-bit challenge response for the challenge for the second multiplexer. Total 16 inputs, 8 inputs are there. Accordingly, you will get either 0 or 1. So total, you can find how much combinations you have. So the challenge response pair, simply you can design how like, so ultimately how good your puff is depends how many higher number of CRPs you have. Okay, so let us try to see some other variations. I'm giving the direct research problem to you, right? Someone who are working in the puff, they will directly research problem from here only. So they can they can publish the work, write my name. Okay. Okay. So let me tell you what possibilities are. Yeah, let me go to the next slide, then I will tell you that thing. Okay. I will give the open problem. Those who are working in puff, be careful what I'm saying here. Okay. Yeah, this is nothing but this is a simple CMOS inverter. Okay. But it is not necessary that whatever the ring oscillator you are making, you can always make with the CMOS inverter. You can change this inverter. If you are using this inverter like a tri-state inverter or XOR gate, might be they are more configurable, more variations may be possible. Okay, and they can give you the most challenge response pairs. Okay, so yeah, so there are some challenges of this conventional RO puff. What those challenges are? Less configurability. You can see, like you can find only, even after making these many circuits, I am getting only 16 challenge response pair. This is very less number. I can predict what could be the possible CRP. So you need large CRP to decide, okay, to authenticate your chip or to make the security, to maintain the security of that chip. Yeah, the very less CRP, and aging effects are more. What is the aging effect? Let me briefly start with the aging effect. Okay, aging is nothing but like with the elevated temperature, with the time, the performance of your. Hello. Okay, so with the at the elevated temperature and with the time, the behavior of transistor changes. Okay, let us assume simply saying like if I am using the normal CMOS circuit or PMOS transistor, so there must be some impact of NBTI and the PBTI. The simplest impact of the NBTI and PBTI are they increase the threshold voltage with respect to time. Okay, if they are increasing the threshold voltage, the operating frequency of your ring oscillator will also change. So might be it can create a problem. Whatever the frequency I was expecting before, maybe it can change. I am going to answer his question now. Okay, let us assume if I have 2 ring oscillator, this one and let us assume the 17th one, and I know that this particular RO is faster than this one. Okay, and this will remain same because I have already fabricated it. This will remain same. Only now CRP depends on what challenge you are giving. Let us assume the first ring oscillator is faster than the 17th one. Okay, so here let us assume this is the first one, this is the second one. But what happens with respect to time, their frequency may change. Their frequency may degrade. Okay, even though they are degrading the frequency, still I'm getting like the frequency of the first one is higher than the second one, so counter will accordingly reach to the same response only. It will give the same response. This particular variation is because of the aging effect or because of the NBTI and other things. Now let us see the second thing. If I have the first arrow having more effect of the process, having more effect of aging, having more effect of NBTI, and the rate of change in the frequency is more, after certain period of time might be they can flip their frequencies. Frequency can change. So previously I was getting for the same challenge I was getting 0 response. Now for the same challenge I will get the 1 response, which is incorrect. So this is not required one. So this is what you ask the question, like how I should maintain. So at the time of designing, I should see like how much reliable or aging resilient my inverter is, so that the ring oscillator frequency should not degrade in such a way that it should flip or it should change this status. Okay, समझ में आ रहा क्या हो गया? Okay, so this is really very important thing that you should know. So how to do that? The question is how to achieve this aging resilient ring oscillator. So there are a lot of architectures, lot of circuits. They are utilized. If so, ultimately, let me go into more detail. Should I go into detail? I don't know. But someone may say what we are teaching. You are talking about your research then. Leave it. Okay. If you are interested, come to me. I will explain in more detail. Don't worry. Fine. So I was talking about the configurability. Okay. So if I want to increase the challenge response pair, more number of challenge response pair if I need, how I can do that? The first and very important way is utilizing the configurable kind of circuits. I know that XOR gate, 2 input XOR has 2 inputs. Of course, 2 inputs. There are 2 inputs, and if I can fix one of the input to logic 0 or 1, it can either act as a buffer or inverter. You know this property? Okay, so it can act as a buffer or inverter, and we are utilizing the inverter to make the ring oscillator. If somehow I'm fixing one of the input either to 0 or 1, I can decide whether it is acting as an inverter or buffer. That's fine. So maybe if now here is the catch. If I'm using my XOR gate like a buffer, it will have a different behavior. And if I'm using like an inverter, it will have a different behavior, different variation effect. Okay, so even though by configuring this thing like an inverter or buffer, you can get a different variations, and possibly the frequency of your ring oscillator will also vary by configuring these things as well. So if you are using this configurable kind of things, so here those input itself can act as a challenges. So here instead of giving challenge to only the multiplexer input, you can give challenge to one of the input of XOR gate as well. So your number of challenges are being increased, so CRP will be very high. पता नहीं समझ में आया कि नहीं आया क्या होगा? उड़ गया ऊपर से. चलिए आगे देख. Okay, so let us try to see what is happening here. One of the possible design of CRP could be like this. Could be the configurable arrow, where you have the challenge here as well, not only in the multiplexer, you have the challenge here as well. So the number of challenges are being increased. Similarly, the CRP will be very high. And these challenges are given from the LFSR only. They are being generated from the LFSR. Okay. The same challenges are given to this one. Counter is there. Yeah, I have taken it from my paper only, so that's fine. And then you can compare which of the counter has. Now here is the catch. Catch is maybe this counter can reach to 111 early than this one, or this can reach to this one. So this comparator I can decide. Either directly I can take this as output, so I will get 32-bit response. These many challenges, these many responses, so you can increase the CRP to the very high value. You can take this as this one, or there be possible you can add these two and then consider it as a responses. So there are a lot of possibilities. You can add these two numbers. You can find the largest number as a response, smallest number as a response, slower RO as a challenge response, faster RO as a response. So there are a lot of permutation and combination. With all combination, you can get the unique responses. So ultimately you are trying to get unique challenge and response pairs. Okay, so architecture can be changed, and accordingly you can get the output. Yeah.
One doubt now. We know that for this circuit to oscillate, there has to be odd number of inverters in the feedback loop. So if I make one of the XOR gate to act as a buffer, it will make even number of inverters.
Then we have to be careful about there should be odd number of XOR that should behave like an inverter. So that's important. So here you have to decide your LFSR in such a way that you should get like that. So if you are getting like a even number of, then you have to make any one like an inverter or buffer so that you can get the odd number. So that's also important. Yeah, very good question. Okay. Okay. Similarly, you can utilize the tri-state inverter. Tri-state inverter has one that can make your circuit in high impedance state. Either it can act as an inverter or in high impedance state. That's also one of the possibility that you can utilize it, where you can have the more configurability, just like the conventional one, but utilizing the tri-state one. Similarly, you can utilize this tri-state like here, and you can change the architecture. So there are a lot of possibility that you can do that. Okay. So read my paper, extend it, cite my paper. That's enough. Okay. So with this one, yeah, so there are some focus issues that we have focused on this kind of like that we have tried to achieve it, like configurability is more, power efficiency, security primitives. So these are some of the key benefit of it. Okay, so I think I should hand over this lecture now to him because it's already 2.5 hours. Other things we can discuss in the next lecture because I am again going to take 2 more lectures. Okay. Yes, please go ahead. Questions are always welcome. I like questions. Not silly, nothing is silly. Please.
So I'm taking 1000 transistors for 2 years. It is a part of that IC.
Okay.
So it gets, I will get different response. If I will take another 1000, I is keeping this 1000 transistor and taking another 1000 transistor, then I will get the response differently.
Yes, I agree.
Right. So I can check multiple possibilities in the chip on which portion I can put this. If I want to clone IC, same IC, if I check another IC, if I have a challenges, I have a response. I know this is the identification of this IC, but I am making a clone IC, and I am checking the possibility. Thousands of available portions, and if somewhere it is matched, then
so this is what the machine learning attack based model. What they have the challenge, they have response. They can simply by simple model, they can predict what is the responses. So for that, if you have large CRP, predictability will be less. But you have very less CRP, it's possible it is predictable. There are some work in the same paper. Might be I have cited somewhere. Here, no, not here. Oh, sorry. Somewhere. Yeah, in this paper we have done this. So we have tried to predict the CRPs as well with some machine learning attack model. So you can predict it. If you are not able to predict the responses, it means you have designed very good path. So that's possible. For every benefit, there is always a problem. So let us assume I have a biometric. There are many things like you can stick something and then again put it something. I don't know, movies where you have seen it, right? So that's also possible. This is what the cloning is. That's all.
Challenges I have a response. So I can develop that model for my requirement.
Yes. Completely agree. I completely agree. See, if you are able to predict the responses, definitely you can use, okay, if I will give this challenge, this response should generate. So instead of using the puff, I will directly give the same challenge and I see, okay, this response should come. I will apply this response and that I can utilize that chip. So that's possible. Yeah. Clone, no. Clone is different thing. Cloning means even though you are cloning like the design cloning, but you cannot clone exact puff. here are two things. You cannot clone perf, but the thing is, you can match the exact responses. You can match by some mathematical model, not by the transistor utilization. So you are talking about, can I use a 100 set of transistors and generate the same response? No, that's not possible because that's a different perf. But to get the same response with the some model, that is possible. That is possible. In chip, not possible because chip is already fabricated. Chip is already fabricated, so you cannot add it. Na? Once it is done, you have only the input and output, challenge and response. So you can just predict it after fabrication. Whatever at the time of fabrication it was, it will remain same. I'm expecting it should remain same.
I will check that.
Yes. Yeah, if there is no process variation effect, temperature effect, or the aging effect, so it should be same. And again, but you cannot develop the same perf because that perf is utilizing the inherent process variation. So you cannot create the same variation at the time of fabrication of another chip. So that's not possible. Okay. So with this one, I'm closing the session for the day. In next lecture, I will continue with the arbiter perf, and I will try to explain what parameters need to be considered if I am trying to evaluate the physically unclonable function. Thank you so much. Okay, so let us take a break of 5 minutes, and then maybe you want to continue for 1 hour. No? So we'll start at 45, and we'll close at 12:35. 12:35 to 12:40. So we'll have 1 hour.
To switch from security back to insecure